amount of air that you normally move in and out during a normal breath, right? But you could, if you wanted to, take in a deeper breath than you normally do. And you could, if you wanted to, expire more air than you normally do. Okay? So these are the different volumes we want to test with your lungs. How much air you move through your lungs in a normal breath, and how much air you can move through your lungs in a maximal breath. You take a maximal inhale and a maximal exhale. So what we would do to test this in the lab is we hook you up to the spirometer, so you have a mask on that's measuring the airflow in and out, and it's connected to a graph. Okay, so as you inspire, the pen moves up, and as you expire, the pen moves down, so you're going to get a curve as you're breathing. Okay, so we'd hook you up, we'd have you take a couple of normal breaths, then we'd have you take a maximal inhale, as much air in as you can, and then a maximal exhale, blow it all out. Okay, let's do that together. Sit up, put your feet on the floor, with your mask. Take a couple of normal breaths. And then when you're ready, take in a maximal breath. You're going to want to do it through your mouth. Take in as much air as you can. Expand your lungs. In. When you think you can't take it anymore, try to take in a little bit more, and then forcefully blow it out. And then keep squeezing until you try to empty your lungs completely, and then go back to your normal breathing. Okay? So, you end up with a curve that looks like this. Normal breath, maximal inhale, maximal exhale, normal breath, normal breath. Okay, so I'm going to draw a line across the top of the normal breath. I'm going to draw a line across the bottom of the normal breath. I'm going to draw a line across the top of the maximal inhale. And I'm going to draw a line across the bottom of the maximal exhale. I'm going to name these lung volumes. So, this smaller curve here was the amount of air you moved through your lungs in a normal breath. So that is called the tidal volume, T-I-D-A-L, like a tidal wave. Tidal volume is the amount of air you move through your lungs in a normal breath. Tidal volume is the amount of air you move through your lungs during a normal breath. But you could take in more air than that if you chose to. So you have a reserve amount of air, right? So beyond the air that you normally breathe in, you have a reserve amount. So this is your inspiratory reserve volume. Inspiratory reserve volume is the amount of air you could inspire beyond a normal inspiration. Inspiratory reserve volume is the amount of air you could inspire beyond a normal inspiration. We put those together, we call that your inspiratory capacity. So we could say that inspiratory capacity equals tidal volume plus inspiratory reserve volume. Questions on that? Okay, I'm going to go over here. So these curves are the same as these curves, right? They're just normal breaths. So I'm just moving over here because I'm running out of space over here. It's not that these are inspiratory volumes and these are expiratory volumes. It's just that I'm spreading them out. Okay, they're the same breaths. So you could expire more than you normally do. That's your expiratory reserve. Expiratory reserve volume. The amount of air you could expire beyond a normal expiration. Expiratory reserve volume is the amount of air you could expire beyond a normal expiration. When you do your maximal expiration and you blow out as much air as you possibly can, do you think your lungs are empty or do you think there's a little bit of air left in? A little bit of air left in. We can never get all of it out. Just like when we squeeze the ventricle, we're trying to empty it, but there's always a little bit of blood left in. What's the term for the amount of blood that's left in the ventricle after we empty it? End systolic volume. Okay, so the amount of air that's left in the lungs after we empty them is residual volume. Residual volume is the amount of air left in the lungs after a maximal expiration. Residual volume is the amount of air in the lungs after a maximal expiration. If we combine those two together, that will be called your functional residual capacity. So, functional residual capacity equals what? Respiratory reserve volume plus residual volume. Okay, two more. From the top of your maximal inhale to the bottom of your maximal exhale, that is your vital capacity. So vital capacity is the maximal amount of air you can move through your lungs in one breath. Vital capacity is the maximum amount of air you can move through your lungs in one breath. So we took a maximal inhale and a maximal exhale. And that volume of air was our vital capacity. Maximum amount of air you can move through your lungs in one breath. Can you give me a formula for vital capacity?
IC plus FRC.
Inspiratory capacity plus functional residual capacity wouldn't work because that includes residual volume. Expiratory reserve plus inspiratory capacity would work. Or you could do tidal volume plus inspiratory reserve volume plus expiratory reserve volume. That would work as well. Okay, if we do include residual volume, that would be called the total lung capacity. So give me a formula for total lung capacity.
Oh,
A few different ways you could do it.
RV plus VC.
Okay, so vital capacity plus residual volume would be total lung capacity. Can you think of another way to do it?
IC plus FRC.
Inspiratory capacity plus
FRC.
functional residual capacity, and there are other ones you could do as well. So there's not just one correct way to write a formula as long as they make sense. It's fine. Okay, so you need to be able to draw and label this graph with these lung volumes and know the definitions. I believe I have this graph on Canvas for you. I think it's in the chapter 8 module and it says lung volumes and it's just a handout of this. So typically in the past, the way I've done this is ask you to draw and label it, but you don't have to write the definitions on it. I ask you about the definitions and the formulas separately. But you should be able to draw and label it and write these terms out. Yes.
When we draw this, what do you want us to like label the dotted lines as?
I'm not labeling the lines as anything. But when you draw it, this curve that we drew was drawn in a very specific way. So what I've seen before when I ask people to draw this is they just do a curve like this, and then they start labeling things and it doesn't make any sense. Okay, these curves are very specific with an inspiration, a maximal inspiration and a maximal expiration. So you can't just start doing random things and labeling them. It has to match on the curve what it means. Yes, go ahead,
To
Gabby.
be more specific, so after you do your big breath and after you exhale, the breaths after your big exhale, are they gonna be greater than the initial little breaths, or are they
No.
just the same?
Those should be the same as these.
Okay.
Yeah.
Sorry.
That's my bad.
Would it make
It's 3D.
Yeah, no, those should be the same.
Would it be smarter to draw the lines first and then fill it that way?
I mean, I'm not gonna mark off if this happens.
Oh, okay.
It's still reasonable. Okay, any other questions on this?
The worksheet is not
The lung volumes is not? Is it in the first module maybe?
Yeah, it's in the first one.
It's in the first module?
Where all the study guides are.
Solve that problem.
Okay, now we're moving into pulmonary diffusion. What is pulmonary diffusion? Gas exchange in the lungs. Okay, so let me give you a big picture drawing of where we are before I get into details. So here we are again with our lungs. We just talked about how we get air into the lungs, right? Contracting the diaphragm, expanding the lungs, creating a gradient, air comes in. Now, when the air comes into your lungs branch off, right, and get smaller and narrower. And at the ends of these branches, we have our alveola, right? You guys have studied the anatomy of the lungs before. So the alveola is the smallest part of the lungs. So if this is the alveola on the end of the branch, and this is a capillary, this is where the gas exchange is taking place. So you just breathed in oxygen. Now there's oxygen in the alveola. We need the oxygen to diffuse into the capillary, into the blood. This blood is coming from the exercising muscle. The exercising muscle was producing carbon dioxide, and the bicarbonate buffer was producing carbon dioxide. So there's carbon dioxide in the blood that we need to diffuse into the alveola so that we can exhale it. So this is where the gas exchange is happening, deep inside the lungs where the capillaries meet the alveola. Okay, so this is called the respiratory membrane, where the capillary meets the alveola, where the gas is diffused. That's the respiratory membrane. So I'm going to take that and I'm going to zoom in on that. So if this is the wall of the alveola, we call this the alveolar wall, and this is the wall of the capillary. We call this the capillary wall. The alveola has a membrane. We call this the alveolar basement membrane. The capillary also has a membrane. We'll call this the capillary basement membrane. So this whole thing is the respiratory membrane. This is what the gases have to diffuse across. 4 parts of the respiratory membrane: the alveolar wall, the alveolar basement membrane, capillary wall, capillary basement membrane. Okay, so this is the alveola, which is in the lungs. This is the capillary, which has the blood. So we contract the diaphragm, expand the lungs, create a pressure gradient, oxygen comes into the lungs, so it's here. We need the oxygen to diffuse across this respiratory membrane and go into the blood. This blood has carbon dioxide in it that I picked up at the muscle. We need that carbon dioxide to diffuse across the membrane into the lungs so we can expire it. Okay, keep in mind also, we talked about blood flow. It goes through the right side of the heart and out to the lungs, right? And then back through the left side of the heart and out to the body. This is where it's going to go to the muscles that are going to consume oxygen, and then that blood is going to come back into the right side of the heart. So right now we're here in the lungs. So the blood that's coming into the lungs should be low in oxygen and high in carbon dioxide because it's coming from the exercising muscle. Does that make sense? Okay. Questions so far? Okay, so if you're resting, you're still consuming oxygen, but not very much. So the blood is going to flow through your body, and it's not giving away much oxygen because your muscles are mostly resting. So when it comes back through to the lungs, it still has quite a bit of oxygen in here. So you don't need very much, so it's going to diffuse slowly. It's like going to the gas station when you still have 3/4 of a tank. You don't need very much, okay? If you're exercising, the muscles are consuming a lot of oxygen. The blood that comes in here is very low in oxygen. The gas is going to diffuse faster because you have a larger need. There's a bigger difference, okay? So we're talking about a gradient again, a difference in pressure. If there's a lot more oxygen in this area than in this area, the gas is going to diffuse faster.
During exercise.
Which is during exercise, yes. So, the gas is always going to go from high pressure to low pressure. We will never have more oxygen in our blood than we have in our lungs. Because our body's not producing oxygen. We're consuming oxygen. The only place we're getting oxygen from is from our lungs. So there's no way for us to have more oxygen in our blood than there is in the air we're breathing. Hopefully. Carbon dioxide. So oxygen will never be diffusing out of the blood into the lungs. Carbon dioxide, there's very little carbon dioxide in the air we're breathing, hopefully. But our body is producing carbon dioxide. So there should always be more carbon dioxide in the blood than in the lungs, and so the carbon dioxide will always diffuse this way. If you're someplace where there's a lot of carbon dioxide in the air or carbon monoxide, that's bad. Then you're going to have that diffusing into your blood, which is going to bump off the oxygen from the hemoglobin, and you're going to die. But most of the time, it's diffusing the other way. Questions so far? Okay, I have a few laws for you. Dalton's law. I'm going to give you the law and then I'm going to explain it. Dalton's law says total air pressure is equal to the sum of the partial pressures. Total air pressure is equal to the sum of the partial pressures. He left. He doesn't get to be part of my analogy.
I'll tell him tomorrow, don't worry.
I have an analogy for this. 200 pounds. There's 3 of us carrying it. This one's me. I'm a wimp. I'm only gonna carry 20 pounds worth. This one's Talene. She's a beast. She's gonna carry 50 pounds of it. And Sivan, little weakling that he is, he's gonna carry the other 30. I'm only doing that because he's not here. So, each of us is contributing to the lifting of the total weight. Okay? So if we think of this as total air pressure is 100% of the air pressure. The air that we breathe is a combination of oxygen, carbon dioxide, and nitrogen. So each of those gases is contributing to the partial pressure. Sorry, each of those gases is contributing to the total pressure. It's each individual contribution is the partial pressure. Okay? So if this one's oxygen, it's contributing a certain amount to the total pressure. Nitrogen is contributing a certain amount, and carbon dioxide is contributing a certain amount. The more of the gas that's present, the more it's contributing. Okay? So if partial pressure is high of a particular gas, it means there's a lot of that gas present. If partial pressure is low of a particular gas, it means that there's not a lot of that gas present. Okay? So you need to know the law. The main thing you need to know from this is how to use the term partial pressure. Because what's going to happen is, instead of just saying there's a lot of oxygen here, I'm going to say there's a high partial pressure of oxygen. I'm going to write it as PO2. High partial pressure of oxygen means there's a lot of oxygen. Okay, so there's a lot of oxygen in the lungs and not a lot of oxygen in the blood. So there's a pressure gradient. There's a difference in pressure, which is going to cause the gas to diffuse across the membrane down the pressure gradient. Okay, same thing with the CO2. I'll refer to it as PCO2, or the partial pressure of carbon dioxide. PCO2 is higher in the blood and lower in the lungs. Therefore, there's a pressure gradient, and the gas will diffuse down the pressure gradient. Questions on that? Okay. Henry's law. Gas dissolves in liquid in proportion to its partial pressure. Gas dissolves in liquid in proportion to its partial pressure. Where do we have gas dissolving in liquid? The oxygen going into the blood is gas dissolving in liquid. What does it mean to be in proportion to?
The same amount.
It's a direct relationship. So if one is high, the other is high. If one is low, the other is low. As opposed to an indirect or an inverse relationship, or one thing goes up and one thing goes down, like Boyle's law is an indirect relationship between pressure and volume. One goes up and one goes down. In proportion to means they go up together and they go down together. It's a direct relationship. So gases dissolve in liquid in proportion to its partial pressure. Partial pressure refers to the amount of gas that's present. So if there's a high partial pressure of oxygen, there's a lot of oxygen present, you're going to have a lot of oxygen dissolving into the blood. That's all that means. Questions on that one? Okay, last one. This one's my favorite. Fick's law.
You can't change it to flex law just for this
I wish. the rate of diffusion is proportional to the surface area and partial pressure gas gradient. Fick's law says the rate of diffusion is proportional to the surface area and the partial pressure gas gradient. What diffusion are we talking about? The movement of these gases across the respiratory membrane. Oxygen and carbon dioxide is the diffusion we're talking about. What does the rate mean? The speed. So the speed that the gases will cross the membrane is proportional to, what does that mean? Direct relationship. They're up together or down together. The rate of diffusion is proportional to, I'm going to skip the surface area for a second and go to the partial pressure gas gradient. What's the partial pressure gas gradient? The gradient is the difference in pressures between the two areas. So if the gradient is high, that means there's a large difference. There's a large difference, the gas will diffuse faster. Okay, the rate of diffusion is proportional to the partial pressure gas gradient. So if the difference between oxygen content in the two areas is large, the gas will diffuse faster. When will the difference be large? At exercise or at rest? Exercise, because the muscles are going to consume oxygen, so the blood that comes back in here is deoxygenated. So there's a large need, so the gas will diffuse fast. If you're resting, you're not consuming a whole lot of oxygen, so there's still quite a bit of oxygen here. There's not as big of a gradient, it will diffuse more slowly. Yes?
On that surface area, does that mean like, I know in the lungs we have like surfactant, so if we don't have as much surfactant, it's gonna be harder for it to dissolve or cross because the surface area is smaller?
I'm not sure about that. Okay, so the rate of diffusion is proportional to the partial pressure gas gradient. It's also proportional to the surface area. So the surface area, in this case, is referring to the respiratory membrane. So, if this is the alveola, and this is the capillary, right here where they meet is the respiratory membrane. So, if you're trying to go into a concert and they only have one metal detector open, only one person can go in at a time, and there's a really long line. But if they open 10 more metal detectors, then we have more surface area devoted to respiratory membrane, and more oxygen molecules can diffuse at the same time. More people can go into the concert at the same time, so it's going to be faster. Okay, so surface area refers to how much space we devote to respiratory membrane. So instead of one oxygen molecule crossing at a time, we can have 100 oxygen molecules crossing at a time. Go ahead.
So type 1 fibers will have a ton more of that surface area.
Well, right now we're in the lungs,
Oh, right.
but this is also true in the muscles, so yes. That's another reason we get more oxygen delivery to the type 1 fibers. Yep. Okay, so Fick's law, the rate of diffusion is proportional to the surface area and the partial pressure gas gradient. So the gas will diffuse faster if we have more surface area devoted to respiratory membrane, so more molecules can cross at the same time, and if there's a larger gradient, gas will diffuse faster. Everybody okay with that? Okay, so you need to know all those laws, how they apply to pulmonary diffusion. You need to know the 4 parts of the respiratory membrane, where the gases are diffusing, how we get them to diffuse. Any questions? Okay, then we're on to transportation. erase this? Did you guys get a picture of it? So, through inspiration, we got oxygen into the lungs. Through diffusion, we got oxygen into the blood. Now we need to get it to the exercising muscle. So, most of the oxygen that's in the blood is bound to hemoglobin. When the hemoglobin has oxygen attached, it could be called oxyhemoglobin. When the hemoglobin does not have oxygen attached, it might be called deoxyhemoglobin. You'll see those terms in the book. I don't use those terms a whole lot. I prefer the term saturation. Hemoglobin saturation. So if saturation is high, it means hemoglobin is holding on to a lot of oxygen. If saturation is low, it means hemoglobin is not holding on to oxygen, it has released it. Okay, so if saturation is high, hemoglobin is holding oxygen. Saturation is low, hemoglobin is not holding oxygen. Okay, low hemoglobin saturation is not necessarily a bad thing. It just depends where the hemoglobin is. When the hemoglobin is going through the lungs, we want it to be fully saturated. We want it to grab onto as much oxygen as it can. But when it gets to the exercising muscle, we want it to release so that the oxygen can go into the muscle, into the electron transport chain, so it can combine with hydrogen and produce water. Okay, the hemoglobin has to release it for it to do that. So hemoglobin releasing oxygen is not necessarily a bad thing as long as it's doing it in the right place. Okay, so we need a system in place to signal to the hemoglobin when is the right time to release its oxygen. Okay, so we need to talk about factors affecting hemoglobin saturation. So, if this is the muscle, this is the capillary, and we've got hemoglobin here bound to the oxygen that's coming towards the muscle. If this muscle is exercising, what are some conditions you'd expect to see around here?
Lactic acid. Lowered pH, increased hydrogen ion capacity.
I already have increased hydrogen. What else?
Lowered pH,
Decrease in oxygen.
increase in CO2,
Okay, but I'm now going to put PO2
and increase in
and PCO2 instead of just O2 and CO2. Okay, so the exercising muscle is creating these conditions. So when the hemoglobin arrives here, these conditions are going to be a signal to the hemoglobin, this is where the oxygen is needed, this is where I want you to release. Okay, so this hemoglobin is going around, and at your resting muscles, it's going to keep holding the oxygen for the most part. It's going to release a little bit, but it's going to keep holding it till it gets to an area that convinces it that there's a large need, and then it's going to let go. So, first factor affecting hemoglobin saturation is going to be the partial pressure of oxygen. Specifically, a low partial pressure of oxygen will cause a decrease in hemoglobin saturation. This makes sense because PO2 is low at the exercising muscle because the muscle is consuming oxygen. So the hemoglobin arrives here and says, oh, you guys are really low on oxygen, I should leave you some. And it's going to release it. And then it's going to go on its merry way without the oxygen. it's gonna release the oxygen right here. Okay, so there's a graph for this. X-axis is gonna be partial pressure of oxygen, low, medium, high. Y-axis is going to be percent hemoglobin saturation, low, medium, high. So when PO2 is low, how would you describe hemoglobin saturation? Low. Low PO2 is going to cause low saturation. When PO2 is high, how would you describe hemoglobin saturation? Okay, so those are your data points, but it's not a linear relationship. It's a sigmoid curve. So when we read this graph, we actually read it in this direction because if we're following a molecule of oxygen starting at the lungs, the hemoglobin at the lungs is going to be fully saturated. PO2 is high there. That's the highest place, PO2. So hemoglobin is going to be fully saturated. Now hemoglobin is traveling through your body. As it approaches the exercising muscle, PO2 is low. It's going to begin unloading its oxygen until it's unsaturated. Okay, so PO2 is high at the lungs. Myoglobin is fully saturated. Hemoglobin is fully saturated. When the hemoglobin arrives at the exercising muscle where the PO2 is low, it's going to release its oxygen. This is exactly what we want to happen. This is how we deliver oxygen to the exercising muscle. Noe?
So when we have low hemoglobin saturation, it means that we want it to happen at the muscles because it's going to drop off more oxygen.
Yes. We don't want to have low hemoglobin saturation in general. We just want low hemoglobin saturation at the exercising muscle. Yeah. Questions on that? So I typically call this the hemoglobin saturation curve. I think your book calls it the deoxyhemoglobin saturation curve. Either way is fine. Okay, second factor affecting hemoglobin saturation will be blood pH. Okay, so if you understand conceptually what's happening here, the conditions at the exercising muscle are triggering the hemoglobin to release its oxygen. So use your critical thinking to figure out how pH will affect hemoglobin saturation. What kind of pH will cause a decrease in hemoglobin saturation? A low pH. A low pH will cause a decrease in hemoglobin saturation. That's helpful because the pH is low at the exercising muscle because of the hydrogen from the lactic acid, right? So when the hemoglobin arrives to this exercising muscle and the pH is low, that's its trigger to release the oxygen. So this muscle can continue exercising. There's a graph for that. This graph is going to start out looking exactly like this one. It's still going to have PO2 on the x-axis. Low, medium, high. It's still going to have percent hemoglobin saturation on the y-axis. Low, medium, high. I'm going to draw this same hemoglobin saturation curve, but I'm going to label it as normal pH, and then I'm going to draw another curve and label it as low pH. Okay, so the same curve, PO2 is low, hemoglobin saturation is low, PO2 is high, hemoglobin saturation is high, and it's a curve. And we're going to call this normal pH. The curve for low pH is going to match this curve. It's going to be the same curve. It's either going to be shifted above this curve or below this curve. Which one is it going to be?
Below.
Below, because as we move up on this graph, it's an increase in saturation. And a decrease in pH is causing a decrease in saturation. So this curve needs to be below the other curve. And this will be low pH. Yes?
This often makes sense, right? Because the Fick's law says that it has to relate to surface area, and in surface area, we have the vasodilation at the muscles because of the intrinsic control, which is expanding and allowing it to be able to go through, and because of those conditions, it decreases the pH, all allowing this so that we could get more oxygen.
More blood
to the
flow.
muscle.
Yep. Okay, so if you look at this graph, we're talking about pH, but we still have PO2 on the x-axis. So what this really means is I could select any PO2. Let's say I select a medium PO2. At any PO2, if I select this one, hemoglobin saturation is going to be lower where the pH is lower. Okay? You don't really need to worry about that. Just understand that this graph shows that a decrease in pH will cause a decrease in hemoglobin saturation. That's important because it allows oxygen to be dropped off at the exercising muscle where the pH is low. Okay, this curve has a name. It is called the Bohr effect. The Bohr effect is specifically the effect of pH on hemoglobin saturation. So the Bohr effect will be that a decrease in blood pH will cause a decrease in hemoglobin saturation. And by the way, I forgot to say, when you draw these curves, you have these 2 points. It's important that you don't draw the curve this way, because this would mean there's a rapid decrease at first and then it slows down. And that's not what's happening. We've got a slow decrease at first and then it speeds up. So you got to make sure you draw the curve in the right direction. Questions? Okay. Third factor affecting hemoglobin saturation will be temperature. Use your critical thinking skills to figure out how temperature will affect hemoglobin saturation. Increase in temperature will cause a decrease in hemoglobin saturation. Increase in temperature is one of the conditions at the exercising muscle. So when the hemoglobin arrives here, that's another signal to tell it this is where we need the oxygen to be dropped off. I'll draw a graph for that as well. It's going to start out the same. VO2. Low, medium, high. Percent hemoglobin saturation. Low, medium, high. PO2 is low, saturation is low, PO2 is high, saturation is high. Sigmoid curve, and I will call this one normal temperature. And then I've got to draw another curve for high temperature. It's going to be the same curve, but it's going to be shifted. Is the curve for high temperature going to go above this curve or below this curve? Below. Just because it's high temperature doesn't mean it's going to go higher on the graph. High temperature is going to cause a decrease in saturation, so it's got to move down. Increase temperature. So notice that temperature has an inverse relationship. Temperature goes up, saturation goes down. The other two have a direct or proportional relationship. They both go up, they both go down. Any questions for me? Okay, so you have 3 graphs here that are similar, but not exactly the same. You need to be able to draw and explain them all. So you need to be able to draw the graph, you need to be able to explain what the graph means, and you need to be able to explain the importance of it. So for example, the Bohr effect. This graph says that a decrease in pH will cause a decrease in hemoglobin saturation. That's what the graph says. The importance of that is that it allows hemoglobin to be dropped off at the exercising muscle where the pH is low. Okay, so you gotta explain what the graph says and explain the importance of it. The importance of all of these are the same. They're all causing the same thing, hemoglobin to be dropped off at the exercising muscle. All right, we are ready for capillary diffusion. What is capillary diffusion?
Gas exchange with the muscle.
Gas exchange with the muscle. So, again, here's the muscle, here's the capillary. I guess I don't need to draw it again, I have it right there. We've got the hemoglobin coming in with the oxygen. We've got this exercising muscle creating all these conditions. So it's gonna drop off the oxygen and leave. We can't do anything with the oxygen right there. Where do we need the oxygen to be? How do we get the oxygen to the mitochondria? Myoglobin. So, myoglobin's job is to pick up the oxygen that the hemoglobin released and deliver it to the mitochondria. The problem is that all of these same conditions are happening that are causing hemoglobin to release the oxygen. So if myoglobin feels the same way as the hemoglobin, the myoglobin's gonna say, I don't want it either. And it's just gonna sit there. So myoglobin needs to behave differently in these conditions than hemoglobin does. So that myoglobin still has an affinity for oxygen. It still wants to pick up the oxygen even when hemoglobin no longer wants it. Okay, so I'm gonna draw the myoglobin saturation curve. When we draw the myoglobin saturation curve, we also draw the hemoglobin saturation curve so we can compare them. So it's gonna start out the same. PO2, low, medium, high. This one's just gonna be percent saturation, not percent hemoglobin saturation, because I'm gonna draw one line for hemoglobin and one line for myoglobin. So for hemoglobin, PO2 is low, saturation is low, PO2 is high, saturation is high, curve, this is hemoglobin. Myoglobin is gonna remain fully saturated. As hemoglobin is releasing its oxygen, myoglobin is loading it. So hemoglobin is going to remain fully saturated until it gets to the mitochondria, and then it's gonna release all of its oxygen. So when the hemoglobin approaches the exercising muscle where the PO2 is low, it no longer wants the oxygen, it's gonna drop it off. Myoglobin retains its affinity for oxygen even in low PO2. So it's gonna pick it up. That allows the myoglobin to deliver oxygen to the mitochondria. Okay, when you're describing this to me, please don't tell me that the myoglobin is delivering oxygen to the exercising muscle. By the time the myoglobin gets the oxygen, it's already inside the exercising muscle. Where is the myoglobin delivering the oxygen to? Mitochondria. You've got to be more specific. Questions on that? Yes?
So although the hemoglobin has a low affinity to oxygen, as soon as it gets to the cell level, myoglobin will still maintain the same level.
Yeah. So myoglobin and hemoglobin respond differently under those same conditions. If they didn't, we wouldn't be able to get oxygen to the mitochondria. Okay, I have one more term that I'm gonna go over and then I'm gonna be done. But I'm gonna do the same drawing again. So this is the muscle. This is the hemoglobin carrying the oxygen. Okay, let's say we bring in 20 milliliters of oxygen to the muscle. These are arteries. These are veins. In the venous blood, we have 15 milliliters of oxygen. Can you figure out how much oxygen the muscle consumed?
Yes.
How much?
5 milliliters.
How'd you figure that out?
Exactly.
So you took the oxygen content of the artery minus the oxygen content of the vein to figure out how much oxygen the muscle consumed. Okay, there's a term for that. It's called AVO2 difference. AVO2 difference is the difference of oxygen content between the artery and the vein. AVO2 difference is the difference in oxygen content between the artery and the vein. It tells you how much oxygen the muscle consumed. So the amount of oxygen coming into the muscle is not likely to change a whole lot, but if this muscle is exercising, it's creating those conditions, more oxygen is going to be dropped off here and consumed. So this number might be lower. So what happens to AVO2 difference when you're exercising? Does it go up or down? It goes up. Because more oxygen has been consumed. So there's a larger difference between the oxygen content in the artery and the oxygen content in the vein, because the muscle consumed more oxygen. Okay, that's a super important concept that we're going to talk about a lot for the rest of the semester. AVO2 difference. Difference between the oxygen content of the artery and the oxygen content of the vein gives you information about how much oxygen the muscle consumed. So it will go up with exercise intensity. All right, do you guys have any questions for me? Okay, I think we have a couple more terms that I'm going to go over in this chapter, but we're basically done. And we are a full week ahead, which has never happened before. So what I'm going to do is that means that next week I'll have a couple of terms to go over with you, and we're going to be reviewing all of next week. But I'll be answering questions. It's going to be really informal, and I'll go over things. We can practice the math, all that. Following week, first half of class is our Jeopardy review. Second half of class is your exam. Okay, so there's not going to be a whole lot of new content next week. We'll do mostly review. Okay?